No. Okay. Can all hear? Hi, good morning. Sorry, I just finished another class. Test. Can all hear? Can see the screen? Testing. Okay, I think you all can hear it. Okay. Let us start the lecture today. So on Tuesday, I have covered the tree structure. And tree structure, I have shown you that you will find that this tree structure, or later the second half you learn about the graph. One of the things you want to print, you want to search the nodes in the tree, you want to print all the nodes in the tree, or you want to count the number of nodes and so on and so forth. All this, one of the common things, the common problem is you need to visit every node once and visit all the nodes once. So we need a systematic way to visit every node once. In that case, it is a traversal problem. And we have covered two type of traversal. One is the depth first traversal, and the other one is the breadth first traversal, or level by level traversal. So in the depth first traversal, we have introduced you, there are three way. One is the pre-order, as you can see in this example. I'm trying to visit every node in this tree, and then I'm using the pre-order depth first traversal. In that case, that means I do my job, I do my print job first, and then followed by visit the left subtree, and then visit the right subtree. So if that is the case, you expect I will print the E, I will print the root. Root will be the first nodes I will print, and then followed by visit the left subtree. After visit the left subtree, I will print the root of this subtree, which is B. And then I will go and the left subtree of the B, which is moving to A, and print out A. Since A, you expect that after they print out the A, they check the left and the right subtree of A, which is both are null pointer. In that case, they will return. Both will return. After you return, no more left subtree. All the left subtree of A is visited, so-called visited. And all the right subtree of, all the nodes in the right subtree of A, which is just a null pointer, also visited. Then you will just return as well. After that, you will return. B still have a right subtree, haven't visit. You expect that they will run this line. In that case, they will go to C and print C and try the other one. Then after that, the left side no more. Then they try the right side. They will print D. After that, D has no more children. They will return. C, all the children are visited. Return. B, all the children, all the subtree, left and right subtree, both are visited. They will return. So that will be, go back to the root. Root still have the right side. So he will call the traversal again to visit the right subtree. Repeat this procedure. Not surprising, they will print out the G, followed by F. Then after that, left side settle, they will try the right side. Then we'll print out the I. Then the last node will be H. After H is visited, all the nodes are visited once, and then you will return. You'll start return. You will start return. Then eventually you're back to the root, and you will return to the main function. So that is the pre-order depth first traversal. Similarly, I also cover the in-order. In-order, you do the operation, your task, process the data in the middle. That's when you're trying to visit the left subtree first. After you visit the left subtree, you will try to process, and then you will carry on to the right subtree. So in that case, you will not print the first nodes here. You are trying to go to as left as you can. You're trying to move to as left as you can. Move to the left side. Move to the left child. If there's a left child available, you're trying to move to the left until you reach the A. So which is the leftmost nodes in this tree. You keep moving left, 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 left. So this is the leftmost nodes of this particular tree. When you reach this point, you will print because no more left child. So you will return and then you will print. After you print, you will try the right child. In this case, there's no right child for A, so you also return. Then after that, you will return to B. After B return from the left subtree, you will try to process. That's when you will print the B. After you print out the B, you will try the right subtree of B. Then you will go to C. When you go to C, you will try the left side since it has no left subtree. So this one will print the C first, followed by visit the right subtree of C, which is go to D. D don't have left, you will also print out, and then no more right, then also got print. I will just go back to C, then C will return no more. They will return to B. B also all are visited. Left, right, subtree, everything is started. Then I will return to the root. When I return to E, since the left subtree nodes already visited, all of them are visited. A, B, C, D all visited. So E will print it out. After E print out, the next one you will try to visit the right side, right subtree. Then since G has a left child, so you are trying to visit its left child, which is F. F, no more left child, so F will print out. And then no right child, return. G, all the left child is visited, so you will visit G. You are trying to process G, print it out. Then go to try the visit the right subtree. Then this one, you will try the left subtree, which is H. After you print out H, you will return and then print out I. On all the nodes are visited, and then you will just return. Then this is the in-order depth first traversal. Similarly, the last one, post-order. Post-order, that's when you will visit the left child, right child. That's when you are trying to visit the left subtree and right subtree before you process. So this is a recursive one. So that first, but I think in the lab I will release soon. Later I will release it. I will ask you to change this particular implementation into a non-recursive version. And you will find that you need a stack to help you. You can imagine that this particular one, you can have a stack. Every time you're trying to visit, you will try to, when you go to here, you are trying to, if the left subtree is available, that's when this one, you will do it later. You are trying to push it into a stack. I push it into the stack. B, I will do it later, so I will push it into a stack. Then when I reach A, I will push it into the stack. Then after that, okay, let's say I put it into the stack. Then I will visit the left side. Left side no more, I try the right side. Right side also no more. Then when I return, when I reach this point, so-called return, that's when I will pop out the A. So then they will print out the A. Then after that, you return to B. B still have the right subtree, you will carry on. That's when you will still push the C. Then there's a left child, no left child, but there's a right child, you will push the D. Then D, no more left, no more right, you will pop out. Then you will print D. Then after that, you return. There's no more left, no more right. All the left, right childs already visited. Then you will pop out the C and print out the C. And then after that, you will return. Then, actually this is when I use a recursive function, implied that is the computer already implicitly declare a stack pointer to help me to store the order. So I will pop up the B. After that, E still have the right child, so I will carry on. So I will push the G into the stack. I will push the F into the stack. Then F has no more left child, right child, so I will pop up the F and print it out. Then I will return. Then this one still have the right child, so he will push the I. Then they will push the H. Then you will start print H, I, G, pop it up, print it. The last one, you will see that in the stack, the last one, the one first in, last out. So which is E will be the last node in the post order that first traversal. It can be done by non-recursive version. This is the recursive version. You expect that to convert this recursive version to a non-recursive version, you expect you yourself need to explicitly declare a stack to help you. So that is the post order that first traversal. I will let you to practice this in the next week lab section. Okay, so you can see pre-order, in-order, post-order, they will print out in the result will be different. Pre-order, you expect that the root will be print out here. Post-order, the root will print out somewhere here. And then in the in-order, because in-order trying to visit the left child, so the first node it print out should be the leftmost nodes. You keep moving to the left. So when you reach the leftmost nodes, there's no more left child. Then you will print it out. So A will be the leftmost nodes. So from the output, you can read from the output to roughly know how the tree look like. But you may not know exactly how the tree look like, but you can know some information. If it's a pre-order, this is the root. If it's a post-order, you know that this definitely is the root. From the in-order, probably you don't know which one is the root, but you definitely know that the leftmost nodes is here. Okay, so that is the different traversal. And all of this can be recursive, can be non-recursive. The implementation can be done by recursive version, you see. In the lab, I will let you practice to implement it in the non-recursive. You expect you need to introduce a stack. So some application, you can use this traversal algorithm to find out the number of nodes. If I want to count how many nodes are there in a binary tree, that means I want to check the size of the binary tree. In this case, that means I will try to visit every node, and every time I visit a node, I just increase my counter by 1. Or my return value, I just let my return value increase by 1. Is there a reason why you would like to use one type of traversal? Depend on the problem. Like in this example, for example, I can choose pre-order, in-order, or post-order. So if I trying to do this way, in this, you can see the result. I'm trying to visit the left subtree first. After the left subtree, as in this one, we're trying to visit the left subtree. Move the left subtree. Every time you move to the left subtree, until you reach one point, no more left child, you're trying to visit the right subtree. No more right child, then you will +1 and return. So that means only one node over there. And then you return. When you return this one, already settle the left child, he's trying to visit the right child. So this is the post-order traversal. And then when you reach this left, no more left, there's a right. Then here also no left, no right child. In this case, you will just simply +1 return. Then this guy, there's a return value from the right side, which is 1. And then the left side, no child, so you will return 0. So 0 plus 1, you get 1. 1 plus yourself. That means, yeah, on this point, I will do the post-order traversal. So I plus 1, so 2. So you expect you will get 2 and return. And then this one will be 2 plus 1 plus 1, which is 4. Yeah, and so on and so forth. So this is a post-order. Well, I can use a pre-order. I will still get the same result. I plus 1 first. Then 1 plus the left sub 3, right sub 3. Then this become pre-order. In order, it also work. So there's no in this particular case, there's no any difference between the pre-order, post-order, or in order. So in order should read the next one is supposed to be G, correct? In order, is it back to, let me go back to the earlier slide. In order, should be after visit E. In order, other visit E, you will go to G, but G have the left child. Yeah, there's a left child, which is F. So he have to visit the F first. Because you need to visit all the left child first, all the left sub 3 first. So G have a left child. So you will visit the G. Then for in order, we implement current to the right first. So we can find the right. Yeah, if you, here is like we visit it, always will visit the left side first. But there's no, this is a general pre-order, in order, post-order definition. But there's no rule saying that you have to visit the left side. Yeah, some problem, if you need, you probably can visit the right side first, also fine. Yeah, that also is another kind of a traversal. Yeah, it's just like normally you find most of the book or website, when they talk about this, they will always start from the left and then followed by the right. Yeah, but there's no any specific reason why. It's just a definition. I define pre-order, in order, post-order in this particular order. Yeah. So is there a big difference in the time complexity between the stack version and recursive version? Technically, I would say there's no difference. But in terms of the, if you're talking about the space time complexity, if you consider the space complexity, time complexity, I think no different. But space complexity, properly you declare your on stack, you trying to use a little bit lesser memory. But overall, the space complexity, I don't think there's big difference. Because when I explicitly declare the stack, I store the minimum data. But for you use the recursive, the computer don't care. The computer have to store all the stacks of this particular function call first. They have to push everything in this particular function call into the stack memory. Because later when you return, have to recover back where you stopped just now, before the function call. Before you recursive call. So they need to store, I expect recursive version will use more memory. But in terms of the space complexity we discussed earlier, we mentioned, it should be still the same. Time complexity, they are doing, you can see that the whole process, there's no difference. So recursive or non-recursive, you will get the same time complexity. And then what else? The time complexity, what is the difference between different? It depends your application, but some question, like you can see in this particular one, it doesn't matter in order, pre-order, because my objective is just want to visit every node. And then every time I visit a node, I just increase my counter by 1 and then return. So I think this one, even you use the level by level traversal, you also can achieve the same result in the end. So it's not, and depend your application. Yeah, some case you can have a lot of solution. in this particular question. So the solution may not be unique. Okay. Yes, the lab test, even the assignment, please don't tell me you coincidentally have the same answer as your friend. It doesn't make sense. Yeah, so should try. In fact, when you practice in your lab, should not just take the answer as a final. Should always trying to think that whether any alternate way to do it. That is like what you're supposed to do and practice. And yeah, not just read the solution itself. You will learn more than just read 10 question solution. Yeah. Always after if you can't do this question, after you see the answer, you should go and think about any alternate way. How about I try this way? If I give you the answer is the pre-order, you should go and try the post-order, in-order. Maybe can I use the breakfast traversal? Yeah. So these are the things you can learn more from a question. So this is a notes. Another one, the example I would like to give you here is the K-level grandchildren. That means if in the earlier terminology, if I call this is the parent nodes, so this is the children. B and F is the children of E. Then A, C, G is his grandchildren of E. Then here I call it is the second level grandchildren, and then this one I call it is the third level grandchildren. Okay, just a name. So now the problem is I give you a notes. Now I give you a notes in the tree. Let's say it's this one. And I tell you my K is equal to 2. My K equal to 2. I would like you to return and tell me all the nodes which is K level grandchildren, which is ACG. Yeah. If I give you K equal to 3, you will print out D for me. So if that is the case, one way is very straight way is hard code it. Yeah. As in you give me a nodes, the left nodes, the left nodes of the left nodes of X, which is the 2 level grandchildren. If there's a left right, also right left, right right. But when your level is 3, yeah, the problem will getting more and more complicated. You expect that first level you have 2 children, then the next level you have 4 cases. Level 2 you have 4 possible case, and then level 3 you got 8 possible case. So probably this is not a very smart way to hard code it. To overcome this, okay, you give me a note. You tell me, okay, initially I let the C start from 0. That means the current nodes is the level 0. Then when I visit C not K is the K is already preset. That means initially I set the K equal unless I pass the argument. So here let's set the K equal to 2. When K equal to 2, that means your C initially is 0. First level you won't print. So you are trying to visit the left subtree. Or after you visit the left subtree, your C will become from 0 to 1. Then after you visit the next level, next subtree, then your C will increase to 2. When your C equal to 2, you will print out, you will print out A. Similarly, you go to the right subtree, your C also equal to 2, then you will print it out. Then here you will do the same thing. Yeah, and then you will start return. If you encounter like F does not have the left subtree, then when you reach the null, you will return, you won't print anything. So in that case, you only print ACG. IK you won't, because at the beginning when I pass, I already start from the nodes E. When I call this function, the pointer at the will point to here already. in this example. So that is something you here in this case I'm using the in-order traversal. Yeah, I'm using the in-order traversal. I think you also can try to see whether you can use the no, this is not the in-order, this is a pre-order. This is a pre-order traversal. Yeah, you also can try in-order, post-order, see whether it works or not. Yeah. Another example, okay, to calculate the height of every node. Okay, this one need to take notes, because different book or online resource, you name it, their definition may be a little bit different. Here, I define that the height of a tree is the number of edge on the longer path from the root to a leaf. So among these, you can see that the longer path is from here to here. So the number of edge, I have 1 edge, 2 edge, 3 edge, 4 edge. So total, I have 4 edges along this longer path. So from the root to the leaf. So in this case, the height of this particular example tree is 4. Okay, so in other words, if your tree only have 1 node, the level is 0. The height is 0. If it's the empty tree, if it is an empty tree, then the height is -1. I define. Okay. Yeah. Because you will find that some book they may define it as the number of nodes. Some define it as a number of edges. Some define it as a number of nodes. Well, both depend. So we have to make if during the test assignment, whatever, if I didn't define the height of the tree, I will use the number of edge as the definition. So please take notes. So in this case, I want to calculate the height of this particular tree. What I will do, I will use here, I'm using the post-order depth traversal. Yeah, this one probably you have to use the post-order because you have to visit the left side and the right side first. Through the left side and right side traversal, you will find out the height of the left side and the height of the right side. After I found out, I compare because you find it's the longer path. So that means the left or right, which one give you, which one the return value is higher, I will pick it. That means the path it should be there. Then plus myself, +1. +1 is due to, for example, this example, here return a value 2. 2 will return back. This one will return 1. Then +1 is due to this edge or due to this edge. You need to +1. There's one additional edge from yourself. So you +1. Either L +1 or R +1. Depend which one larger. In this example, 2 is larger. So it's 2 + 1, 3. So E will become 3. Yeah, the last one here is 3. Here is 2. So 3 is larger. So you take 3 + 1. So the height will be 4. So this is to use the tree traversal approach to find out the height of a. In fact, I can from here I can find the height of every node. Yeah, this one probably is useful for the latter. Yeah, because you always need to know where you are, the height, the position of these current nodes. Yeah, so you can use the height to indicate the level where you are in a tree. So yeah, so these are the traversal. And then next one I'm going to talk about is maybe no, this class. Yeah. So in this part, you have learned about the difference between linked list and the tree. Linked list, stack, queue, circular linked list, doubly linked list, whatever linked list you name it, they are the linear data structure. And tree structure is a non-linear data structure because you have one node, then you can visit the left side, right side. And tree may not be, that is a binary tree. So tree can be have more than one or two children. You can have more than that. Then one of the common problem we need to solve in this tree structure is traversal problem. So here we introduce you the first traversal, pre-order, in-order, or post-order. We also cover the level by level traversal, breadth-first traversal. Yeah, I also show you some example how to use this traversal to solve some problem with the tree structure. And then the new lecture notes. This one. Next topic I'm going to talk about for today's lecture is the binary search tree. So when we cover the linked list, I have introduced you that the linear search. And linear search, you put the data in the linked list and you have no other choice. You have to search every node individually. In the best case, if the item you search key is in the first node, then that is the best scenario. The complexity is constant. But if in the worst case, that means it's in the last node or the item is not in the linked list, in that case, you expect that time complexity will be big theta n. You need to search all the nodes in short. And you will find that also in the average case, yeah, that means the key can be the first one, can be the second one, can be the third one, can be the fourth one, can be any one of the nodes here, or can be not in the nodes in the linked list. Then on average, you will find that it's still in linear. The time complexities overall, the proof have been shown you in the earlier lecture. Yeah, you will find that overall, this kind of a search will take linear time on average. So how can we improve this algorithm? This is something I have mentioned in the earlier lecture. So in this case, yeah, maybe we can, yeah, so someone maybe think that, yeah, since I cover the tree, maybe I can use a tree. But you find that, yeah, this one, just now, this one is inefficient. Okay, you just put the data, instead of put it in linear data structure, you just simply dump the data into tree structure. You find that it's still not, because this way, you still need to visit every node. You can use some traversal approach to search the key, but it still take linear times to search. If the key is the first one, then it's at the root, then you are lucky, then it is constant time. Yeah, should be Anna. I think I copy wrongly. This one should be Anna. Then if the worst case probably depend if it's a pre-order, which one is the worst? Pre-order, you will visit this one, you will visit this one, you will visit. Which one is in the pre-order? If it is a pre-order traversal, I think this one is wrong. I need to update. I found I typed wrongly. Yeah. What do you think? In the pre-order traversal, which is the worst? Which is the last node you visit? Pre-order, you visit first, then you're trying to travel to the left. You visit first, you're trying to visit. So you expect that pre-order. Can I have a pen? You will visit first, then you go to the left. You visit first, this will be the second one. You go to the left, you visit first, you go to no more left, you try the right, no more right, you return, then you try to the right, no more left, no more right, you return. There's a right, you visit first, then there's a left, then this will be the last one. So this is the worst one. Yeah. So this is the pre-order. In the pre-order, this one gives you the best case. This one is the worst. This one is the best. Yeah. So you find that actually by doing so, you didn't improve your time complexity. So then you will find that actually 3 can improve, but it's not enough. You cannot just simply put the data in this manner. So the key is how do we insert the data into the binary tree. If I insert the binary tree, the data into the binary tree in certain order, then I can improve my search time. So therefore, there's a we should trying to sort out the data first. If I sort out the data in this order, I will put all the value which is smaller than the current nodes at the left subtree, and all the value greater than the current nodes at its right subtree, and all the subtree also have the same manner. Smaller value will put it at its left side. All the bigger number will put it at the right side. In this case, I will form a binary search tree. Once you have the binary search tree, and you will find that your search time will be improved. Yeah, later I will show you why. But now you just remember that you just put the value smaller than the current value at the left side, and then those number greater than that at the right side. Why I choose left and right is just a very just very intuitive way. People will choose the left side, put the small number, the right side put the larger number. You also can do it the other way. It's still considered another kind of a binary search tree. Yeah, the algorithm will be still the same, just the left and right you swap it on it. Okay, so that is the binary search tree. Is trying to sort out the data in order so that my search time will improve. Okay, among these 3 examples, are they all binary search tree? Are they all binary search tree? I need to wait for a while. No. Yes. So here, according the definition, you need to take notes that this one yes, this one yes, this one no. There are two issues. The first one is this one. 64. 64 is smaller than 93. 64 is smaller than 73, but 64 is not greater than 70, but 64 is at its right subtree. 64 cannot be here because this one is 70. The right side, no number can be smaller than 70. So this one is not correct. Another not correct note is this one. When we talk about this search tree, there's no duplicate. We're not allowed to insert any duplicate nodes into this binary search tree. And normally you won't store the same nodes into in the same data structure. No point to do so. So this one not supposed to be here. So this node should be not correct. This one should be at the left side instead of the right side. Okay, so this is not correct. The other two are okay. Yeah, even you have this only left subtree data structure, it's also considered a binary search tree. The worst one is, yeah, you have 7, 6, 5, 4, 3. Yeah, this is also considered a binary search tree. Yeah, just like very unfortunately, these three only have one child all the time. Each nodes only have one child all the time. So in that case, too bad. Yeah, it's just like another linked list. So you will find that binary search tree, you are trying to sort out the data. You also need to make sure that the order you insert the tree are well balanced. So we will talk about this thing in this lecture and next lecture. So before that, I just show you that by doing this, let's say I have a well balanced, well nice tree. Then I do the search on this particular tree. It will become a binary search. In that case, the search time will be improved, because by doing this, you can see that in the earlier the tree traversal, I will do 2 recursive call. When now I know that the left side is the number always smaller than the current one, the right side will be always the number greater than the current nodes. So I don't have to visit both subtree to search my key. Let's say I'm trying to search C in this example, and then I don't have to visit the left and the right. I just need to choose one of them based on whether this one is smaller or greater than the current one. So it's either I execute the left child or right child. Then that will reduce my search space. So in this kind of approach, strategy is, you can consider, it's known as a decrease and conquer. That's why I divide my problem into 2 sub-problems, left subtree and right subtree. I don't really solve these 2 sub-problems. I only solve one of them. The other one, I know that it's not possible already. I can eliminate it and throw it away. So that kind of approach is called it as a decrease and conquer. Yeah. For the traversal problem, I will call this thing is a divide and conquer. I divide the problem into 2 sub-problems, and then I need to solve both of them, and then merge the result into a bigger problem. Like what you see, you count the number of nodes. Basically, you divide the binary tree into 2 subtree, and then 2 subtree, you further divide it into 2 subtree. Then after you solve the subtree, the left subtree and right subtree, you merge them. You sum the result together plus yourself plus 1. So this is divide and conquer. But binary search is considered decrease and conquer. I divide the problem into 2. But I know that one of them is not possible. I don't consider it. I throw it away. Then I just only handle the one sub problem. Yeah. Until then, I will carry on my search. Eventually, I search it. I found my search key, or I didn't find my search key. Yeah. So that is the decrease and conquer. So you can find that this search is doing this. Then to insert a node, of course, you have to insert similar to the search, how you search it. So so you need to make sure that when you insert a node, after you insert a node, the binary search tree still as a binary search tree after you insert a new node. And then you need to make sure that no duplicate nodes will be introduced. You need to make sure this won't happen. And then each new nodes will always place to a unique position. Normally they will play, you will insert it, not normally, definitely it will become a leaf in the tree, in this particular binary search tree. So that is the implementation. You can compare with the search algorithm, very similar. you either try to insert the nodes at the left hand side or at the right hand side. You'll keep travel to the left or the right. Every time you just compare the new item is bigger or smaller than the current one. If it's lesser than the current one, you travel to the left. If it's greater than the current one, you are trying to travel to the right. If it's equal, that means this is a duplicate item. So you notice that here, if it's equal, yeah, I won't do anything. I will just simply return. This nodes is already inserted earlier. So you will try to travel until you reach somewhere here. In this example, which is a null pointer. When you reach a null pointer, that means this is the right place for you to insert these new nodes. Yeah, this is how to insert a node into a binary search tree. You can insert, you can search, you can insert. So the next one should be delete. Yeah, I want to remove a node. Then this one is a bit tricky. You want to remove a node from a binary search tree or from a tree. You need to be careful. Yeah, because you expect there are three scenarios. The first scenario is those are in green color. They are the nodes you want to remove. If these are the nodes A, D, G, I, K, M, if these are the nodes, and then this means these are the leaf, and this leaf have no children, so you don't have to worry. Yeah, this one very easy. No children one, you just simply can just remove it, no problem. Just simply remove it, no problem, because they have no any subtree around. Yeah, so you can simply remove it. But the next one, if you look at this one, the second one in pink color one, CFL, which have one child. Yeah, C have one child, D. F have another one child, G. L have one left subtree, but only have one subtree at the left side or at the right side. In this case, you need to swap it. You need to swap their, replace, use the, take out the F. For example, I want to remove the F. I want to remove F. I will take the F out and then replace it by G. Yeah, you move, because luckily you only have one child, so that particular child will replace his position. And then the nodes you want to remove or you want to delete it, you can delete it after that. Same thing, this one, you can replace it by J. Then you can throw it away. C also, you can just remove it, replace by D. Okay, the first two cases, relatively easier. The next one, so for this one, you want to delete it, but those, that means this one, this one, this one, if you want to delete this few, then the problem will be a bit tricky because they have two children. To remove them, how to remove them? So let's say I want to remove the H. If I want to remove the H, how to do it? Here got one subtree, here got another subtree. By doing so, I need to, there are two ways. One approach is like, in the left subtree, I go and search the left subtree. I'm trying to search the rightmost nodes. That means in the left subtree, I visit the right, I visit the right. I keep visiting the right until I reach a null. Then I know that G is the rightmost nodes. What does this mean? G definitely is the largest nodes among these left subtree. A, B, C, in alphabetical order, A, B, C, D, E, F, G. G is the largest one. So once you know the G, you just swap the G with the H. Then H can throw away. G will replace it. G will swap with the H. Then H can throw away. In this case, after you remove, this whole tree is still a binary search tree. The left hand side, all the alphabet A, B, C, D, E, F are smaller than G. I, J, K, L, M is still greater than G. So it is okay to do so. So that is how to remove a node with two children. This is one way. If you don't want to choose the leftmost one, you also can choose from the right subtree. You select the leftmost nodes. In this case, you will choose the I. I, you will find that is the smallest nodes in alphabetical order. I is the smallest one among J, K, L, M. So this is the smallest one. You can also, same thing, you can swap it with the H. If I want to remove H, I swap it with the H. Then I remove the H. Then you will find that it is still after deletion, this new tree is still a binary search tree. So this deletion is valid and okay to do so. Because the right hand sides J, K, L, M are greater than I. A, B, C, D, E, F, G are smaller than I. It's still a binary search tree. So this is how to delete nodes from a tree structure. This one will be in your lab. I will ask you to implement. Therefore, you didn't see any code here. I want you to implement, to consider these three cases. Okay. Maybe I will stop here. The rest part will be talk about the time complexity of the binary search. I will discuss it on Tuesday. Okay. Lab and assignment I will release during this weekend. The assignment 3. I will release it by this weekend. Okay. Any other question? So today you have learned about the, in this week you learn about the binary tree and several traversal problem, depth first search, depth first traversal and breadth first traversal. These two traversal you will encounter it again in the graph, because graph also have the similar problem. You need to visit all the nodes, and each nodes you only wish to visit once. So, and then after that, we use the tree structure to solve, to improve our linear search, which I will we introduce use the binary search today. And next Tuesday, I will show you how the time complexity is improved by using the binary search. So assignment 2 we have finished. I already try to not release too soon. So please try to finish your assignment 2 as soon as possible. Then I will release the assignment 3 soon. So yes, the assignment 2 will be due by next next week, Wednesday. Yes. Is a graph a tree? No, the other way around. Tree is the special case of a graph. You can consider tree is a special case. Graph is even more flexible. Then tree even tree itself also not saying that must be 2 nodes. Must have, only can have up to 2 children. If you have a tree, each node only can have up to 2 children. That is called binary tree. But I can have a trinary tree or whatever number of children tree. You name it. Yeah. So it's not always 2 nodes. It can be 3, can be 4, can be 5 for a tree structure. Just the difference between tree and a graph is graph can have a if you have this thing we call a tree, but this particular is a graph because there's a loop here, there's a cycle here, so it won't be a tree. Yeah, I will always make it as about 2 weeks. The purpose is like you will find that if you don't do the hard question, when you code it, you won't realize that your problem. I can see a lot of people just realize that how to use the debugger, and if you learn, you already took the 103, you're supposed to know how to use the debugger. Of course, when you write the simple question, you won't appreciate the importance to know how to use the debugger, because you always can easily write 2-3 lines, you already finished the question. You have no idea that actually coding, you make a mistake, you need to use the debugger to help you. Okay. Yeah, so I think it's important to, because in the later stage, when you write your program getting bigger and bigger and more complicated application, I think it's not only the debugger. And when you have a big problem, you should not just trying to expect that you can one time finish everything in one shot, that you can just simply type the first line to the line 20, then you can finish the program, and by one click compile you can get the answer. Should learn that how to slowly systematically implement your code, your problem, to solve it, to figure out what are the sub problem, how to implement it systematically, so that it can help you to reduce the implementation time and debugging time. I think I can see a lot of students is like trying to write the code, is one time where we'll write now everything. Yeah, then click compile, then not working, have no idea how to debug. And also later I will make the announcement. So same thing. I think this weekend I also will give I'll try to find some times to go through this week lab section to those people who are not able, due to whatever reason you cannot attend the lab section. Yeah. Okay. Why? Okay. If no other question, that is today lecture. Okay, I will give a Zoom section maybe tomorrow. To go through this week lab. Okay. Okay, thank you, and bye bye.